Okay, welcome to part 2 of our discussion of simple linear regression. Let me just review some of the key things from part 1. What we're interested in is we have a relationship between two variables. The one that we normally plot on the horizontal axis is called the independent variable. And on the vertical axis, we have what's called the dependent variable. We're trying to find a linear relationship that specifies how the dependent variable can be computed from the independent variable. That is, we want to find an intercept coefficient that we're calling beta naught and a slope coefficient beta 1 such that the dependent variable y is given as the intercept plus the slope times the independent variable. We saw through the least squares mechanism that the least squares solution gives us the, I don't seem to be able to highlight that, that's all right, gives us the intercept. B naught hat is the mean of the y's minus beta 1 times the mean of the x's. Beta 1, in turn, is the sum of squares of x times y divided by the sum of squares of x times x. And so once we have this linear relationship with these two coefficients, b0 and b1, from least squares, what we discover is that the actual dependent variable values don't fall directly on that line. There is typically some error or random component associated with each actual y sub I value. Okay, so we call the part of each y sub I value that depends on our two computed coefficients, b0 and b1, we call that the deterministic component. Whoops, highlighting seems not to be working. There we go. So we call the part of each y sub I that comes from our linear regression model the deterministic component, and we call whatever the difference is the error component or the random component. And we are making an assumption here that these random components, good heavens, oh, strange, okay, that these random components are normally distributed with a mean of 0 around the deterministic line and a standard deviation of some sigma sub epsilon, sigma sub error. All right, so that's basically the key things that we talked about, and we're going to continue this discussion in Module 5b here. We're going to take a look first at how the variability of these error values impacts the fit of our linear regression model. We're going to take a look at how to estimate the standard deviation of the error components, given our assumption about these errors being normally distributed around the deterministic part. We're going to interpret what that standard deviation, we're going to interpret what the standard deviation of each coefficient means, the beta naught, beta 1, and also the epsilon, the sigma sub epsilon, the standard deviation of the errors. We're going to take a look at how to do hypothesis testing, interpreting confidence intervals for the regression coefficients, and also discuss and learn how to interpret the so-called R squared, the coefficient of determination of the model. All right, so here is a somewhat better diagram of what our assumptions are about this least squares linear regression model. The dependent value y for each value of x that we have for each of the independent values is going to be given by our beta naught intercept plus our beta 1 slope times the value of x plus some error, epsilon. And so for each x sub I, we're going to have an epsilon sub I error component, which will give us the y sub I. We're assuming, as I said, that these epsilons are distributed normally with a mean of 0 around that regression line and some standard deviation that is the same. So in other words, for each possible value of x. So in other words, these normal distributions of the errors around the regression line for each value of x is identical. Each one of those normal distributions is identical to the others. Now, that may or may not be a great assumption. It could be that as the value of x increases and the value of y increases, it could be that the distributions of the errors spreads out. But we are assuming for this analysis that that is not the case, and that all these standard all these normal distributions are the same. All right, so in this model, in this linear regression model, there are actually 3 parameters that we are computing or estimating. There's the intercept term, beta sub 0, the slope term, beta sub 1, and we're also estimating the standard deviation of these error terms around the regression. Okay, now let's just think about this idea of the standard deviation of the errors conceptually for a second here. We have a couple of scatter plots, A and B here, values of some independent variable x plotted against corresponding values of the dependent variable y. And the question is, given the least squares linear regression for these 2 scatter plots, is the linear regression a better fit of the data in A, or is it a better fit of the data in B? Well, that's equivalent to asking which has less variability around the regression line. Clearly, the errors around the regression line in the scatterplot A are less than the errors around the regression line in scatterplot B. So we're going to say that that this regression line for scatterplot A is a better fit to the data than the regression line around scatterplot B. That is, our error terms in B are much greater. The standard deviation of the errors can be computed easily enough. We just compute each error for the individual sub-i's. All right. Remember that our regression lines equation says that y hat, the predicted value of y, is beta naught plus beta 1 times x. So that's where we get our line from. And then, of course, in real life, the actual values of y differ from those predicted values of y by a certain amount. So here we have, now these are all just shown as epsilon, but here we really have epsilon sub 1 for the error, the difference between the predicted value and the actual value for y1. Here we have E sub, or epsilon sub 2, the difference in the predicted versus actual value of y2. And to get the variance of all these errors, we simply use our variance summation. So the variance is the sum of the actual y sub i's minus the predicted y hat sub i's squared. We're dividing by n minus 2 here because we have two parameters that we estimated from our data set. So we're using n minus 2 instead of n minus 1 as the divisor. And then the standard deviation of the errors is simply the square root of the variances. The differences between the predicted values of y and the actual values of y are referred to as residuals. And so this equation, this formula that we just applied here, produces the standard deviation of those residuals, and this is referred to as the residual standard error. In this particular table, we're showing the kinds of statistics that we would get from a linear regression model run on a regression of salary as a function of years of employment, let's say. So if we have years of employment as our x-axis and salary as our y-axis, we get told here that the intercept, the average starting salary for somebody hired by this company, is $28,394. And then on average, for each additional year of employment, salary is increasing by $1,107. And here we have our residual standard error of the errors of the actual salaries versus the predicted salaries. All right, now the residual standard error divided by the square root of SSXX, which is this sum of these squared terms, each x sub I minus x bar squared. That residual standard error divided by the square root of SS sub xx is the standard deviation of the slope term, beta 1. And this helps us measure the precision, whoa, too much highlighting, the precision of beta 1 hat as our estimate for beta 1. Okay? Let's consider, for example, these two scatter plots that we looked at before. Scatter plot A, in which the actual observations are grouped pretty tightly around the linear regression model. That is the residuals, the difference between the predicted y's versus the observed y's is relatively small. Whereas in scatterplot B, the residuals are much larger. The difference between the predicted y's and the observed y's for each particular value of x is much greater. In which case is the standard deviation of the error terms smaller? Well, I hope it's obvious that the standard deviation of the error terms is much smaller, much narrower in the case of the scatterplot A, or dataset A, versus this dataset B. And therefore, in which case is the standard deviation of the slope, which is the standard deviation of the error terms divided by SSXX, square root of that, smaller. All right, well, the sum of the squares of XX, SS of XX, is the sum of the squares of the difference between the observed x's and the mean of x. Now, it appears to me, and we don't have the actual numbers here, but it appears to me that the mean of the x's is about the same value in each of these scatter plots. And it appears to me that the difference between the observed x's and the mean x are pretty similar. Now, here we have an x that's a bit of an outlier, so it could be that SSXX for B is larger than SSXX for A. But probably those two values are approximately the same, and because the standard error of the residuals is smaller for A than for B, that means the standard deviation of the parameter B, the slope parameter, is going to be smaller for A than for B. In other words, there's a little more wiggle room around the slope found in B here than there is found in A. So in which of these two cases is our estimated B1 a more precise estimate? Well, that's really just an alternate way of asking the question, which standard deviation is smaller. So again, our estimate of B1 for dataset A is going to be more precise than for B. Consider as sample size increases, how is that going to impact the SS of XX? That is, how is that going to impact the sum of the squares of the x sub I minus the x bar? Well, the sum is going to increase as the number of x observations increases, assuming that the general distribution of the xy observations is very similar in both cases, okay? And as the sum of the squares of the x sub I minus x bar increases, that's going to reduce the standard deviation of our slope parameter. All right, so this is yet another case of seeing that as we increase the size of the sample, size, that also has the effect of reducing the standard deviation for our slope parameter. Okay, so now we have our standard deviation for beta 1. We can use that to do hypothesis testing in the same way that we did hypothesis testing for means previously. Generally, our null hypothesis is going to be that the slope is 0, or possibly that it's going to be greater than 0 or less than 0. And our alternative hypothesis then is going to be that the slope is not 0, or if our null hypothesis is that it's greater than or equal to 0, our alternative would be less, and likewise, if the null is less than or equal, then the alternative is greater. And we compute this t statistic, which is our estimated slope minus our null hypothesis slope, divided by the standard deviation of the estimated slope. All right, so this is very similar to the estimated mean minus the hypothesized mean divided by the standard deviation. And the question then is this test statistic enough standard deviations away from 0 to give us to enable us to reject the null hypothesis? We have both two-tailed tests in which we are typically going to just be asking, is the slope, we're going to assume that the slope is 0 and we're going to test whether it's not 0. Or one-tailed tests in which we're going to assume something like the slope, the null hypothesis slope is less than or equal to 0, and the alternative is that it's greater than 0. Okay. Most commonly, we're interested in testing whether the slope is different from 0, either different in either direction from 0, or different in a positive direction or different in a negative direction. Suppose, for example, that our data is showing us years of experience as the horizontal axis and salary as the vertical or dependent axis. Now, we hope that with increasing experience, salary is going to increase. So we hope that the slope B1 here is positive. But of course, as the null hypothesis, we always have to choose the opposite thing. So as our null hypothesis, we're going to assume that in fact, salary does not increase with experience, that it stays the same or perhaps even decreases. Therefore, salary increasing with experience is our alternative. And we're going to use a very strict alpha here of 0.01. So if our t-statistic is way over in this, very far into this right tail, we will reject the null hypothesis and conclude that years of experience does tend to increase salary. Now, we can see the results here in our table that's produced. All right, so let's take a look. Here is the table that we would typically get from any kind of linear regression tool, whether it's ISLE or S or whatever it might be, R. We're not worried about our intercept for this analysis. We're only interested in the slope. And so the idea here is that with years of employment, our estimated slope is $1,107 per year of increased salary. The standard error in that slope is given by the residual standard error divided by the square root of SSXX. All right, so the residual standard error is this thing, 7162, and that apparently divided by SSXX gives us this standard error of $140 per year. Okay? Now, we are doing a test at a significance level of 0.01 in this data set, although we haven't mentioned this before, but in this data set we have 45 people in our sample. Because we are estimating both the slope and the intercept parameters, our number of degrees of freedom for looking up the critical t-value in our t-table is going to be 43 degrees of freedom. All right, so our null hypothesis is that the slope is less than or equal to 0. That is, that there is no positive benefit to years of experience. And of course, our alternative hypothesis is the opposite. We simply look up in our one-sided t-table that the critical value or the cutoff for t at a 0.01 significance with 43 degrees of freedom is 2.42. Then we calculate our test statistic by taking the estimated slope, okay, that's this 107, minus the null hypothesis slope, which is 0, and dividing by the standard deviation or the standard error of the slope, which is 140. And when you do this division, you get this 7.88, and golly gee, that number is also displayed as the t-value in the table. All right, so you don't have to actually do this rigmarole yourself. If you are testing that the null hypothesis is 0, then the t-statistic can be used directly to figure out whether it's not 0. And because 7.88 is larger than our critical value of 2.42, that means that we are, way out here in our right-hand tail, and we can definitely reject the null hypothesis and conclude that that salary does significantly at a greater than 0. Or at a better significance than 0.01 years of experience contributes to salary increase. All right. Let's try a different one. This time, we're going to ask whether a year of additional experience increases salary by more than $750 per year. In this case, the t-values in our table are not going to help us because the t-values in the table assume that our null hypothesis is that the slope is 0. And this time, our null hypothesis is that the slope is less than or equal to 750. Okay? We're going to use a less extreme alpha here. So alpha in this case is 0.05. And we first specify our hypotheses. So our null hypothesis is that the slope is less than 750. And therefore, the alternative is that it's greater than 750. We've got 43 degrees of freedom, 45 people minus 2. And we just look up in our t-table the t with a significance of 0.05, and 43 degrees of freedom is 1.68. All right, so we have to have a test statistics that is out beyond that t of 1.68. And now, as I said, we can't just look at the t's that are in the table because we're not comparing with a null hypothesis of 0. So now we take our estimated slope, we subtract our null hypothesis slope and divide by the standard deviation. In this case, we compute a value of 2.55. And because 2.55 is greater than 1.68, we do reject the null hypothesis and conclude that that indeed the salary increase is greater than $750 per year at a 0.05 level of significance. Now, just out of curiosity, let's go back. Let's see. So our t-value at a 0.01 level of significance was 2.42. That was our critical value. 2.42. All right, so our computed t-score for this revised hypothesis test is also greater than 2.42. So in fact, we can even conclude that that we can reject this null hypothesis at a 0.01 level of significance. We can also compute confidence intervals by basically following the same recipe that we did for confidence intervals around means. So in this case, confidence intervals around the slope is what we're interested in here. So this is going to be some parameter plus or minus some error term. And that error term is going to be the product of the critical t-value times the standard deviation of that, the estimated standard deviation of that estimated parameter. So if we want to get a 95% confidence interval for our experience slope coefficient, we can simply read from the table that the estimated slope is 1107. We can look up, here we want a 95% confidence interval, so we look up the two-tailed t with 43 degrees of freedom and 0.025. Okay, remember that we have 2.5% on the right tail, 2.5% on the left tail to give ourselves a total of 5% in the tails. And that critical value turns out to be 2.02. The standard error is simply given to us in the regression output. And now we just do the multiplication and addition and subtraction, and we discover that the 95% confidence interval for the slope of years of experience, salary as a function of years of experience, is between 824 and 1,390. Notice that both of our previous null hypotheses were below 824, which indicates that we were right in rejecting those null hypotheses at the 5% level in one case and the 1% level in the other case. Okay, well now we're going to ask a slightly subjective question. How good is the model? How well does the model fit the data? We see that the y values, the dependent variables, differ across different observations. And we wonder, in general, how well does x explain or determine the variation in the y. That is, to use specific examples of x and y, we've got our actual data with years of employment and salary as a function of years of employment. And we see at various different years of employment that not everybody's salaries are the same. There's a whole lot of reasons why salaries might differ from one person to another, not having anything to do with years of employment. Level of expertise or the value to the company of the type of work that the employee does, and whether your boss likes you, on and on and on. So it's evident when we look at this regression line that the regression line does explain some of the variation in the y's. With little experience, salaries do tend to be lower than for people who have more experience, and yet at any given level of years of experience, there is variation. Okay, so the conventional way of measuring this variation and the idea of how well does the model explain the variability of y is this thing called the coefficient of determination, or the R-squared. The R-squared is the proportion of the variation in the dependent variable that is directly explained by the regression model. And the way it's computed is you compute, I guess I can't highlight this correctly here. Let me abandon the highlighting. Okay, so remember that y hat sub I is the predicted value of y from a given value of x. And, of course, that predicted value of y for each given value of x is usually not directly equal to the observed value of y. Okay? So, if we compute the sum of the squares of the differences between the predictions and the observed values, the better the model is, the smaller that value is going to be. The better the model is, the closer the predicted values are going to be to the observed values. All right, so we hope for a good model, we expect for a good model that this is going to be a lower value. Now, to normalize that, we are also dividing that by the sum of the squares of the observed values minus the mean of all the observed values. Okay, so this denominator is a normalization factor that ensures that this expression yields a value between 0 and 1. Okay, so the difference between the predicted value and the observed value, that is an unexplained difference. We want the explained difference, and so to compute the r squared, we're taking 1 minus the unexplained variation divided by the total variation. Let's take a look at some examples of r squareds equal to 1. If there is a perfect linear relationship between the independent variable and the dependent variable, so that in your model, every single value of y lies directly on that line and is completely predicted by x, then your r squared is 1. The proportion of the variability in y that's explained by x is all of it. In fact, there is, all of the variation in y is completely dependent on the variation in x. And that's true for a downward sloping or upward sloping y is a function of x. If there is variability, but nevertheless a definite downward slope or upward slope, then our r squared value is not going to be perfectly 1, but it's also going to be greater than 0. So this indicates that there's some kind of strong linear relationship, but not a perfect linear relationship. And in fact, the closer the r squared gets to 0, the less strong is this linear relationship. Okay, so in this case, some fraction, but not all, of the variation in the dependent variable is explained by variation in the independent variable. In the worst case, we have a situation like this where our computed slope is 0, and y does vary, but there's no dependence of the variation of y based on the value of x. This is our worst case scenario. That r squared value is always reported in the output of any regression software that you run. And in this case, where we're comparing the years of employment, the effect of the years of employment on salary, that is, salary is a function of years of employment, this R-squared value tells us that about 60% of the variation in the salary is predicted by variations in the years of employment. Let's go back and look at our plot again. Okay, so about 60% of the variability in the salary levels can be explained by increases in the years of employment. But there is still a lot of variability, so it's only 60%. It's not, 80% or 90%. Okay, so now we get to the value judgment. The idea of the R-squared is to describe how well the model fits the data or vice versa. And so yes, an R-squared of 1 means that the model is perfect, that all of your observations are in a perfect line, and the model completely explains all of the variability in salary based on the number of years of employment. The fact that the R-squared here is less than 1, does that mean that the model is bad? No, it just means that the model reflects the data that you have, and the data that you have has a lot of variability in it, and consequently the R-squared is less than 1. In this case, it's it's about 60%. The question is the model useful? Is the model useful in making estimates about people's salaries based on their years of experience? And I would say the answer is yes. It's useful, but it's not perfect. Okay. You can get a very rough idea of what somebody's salary is going to be based on their years of experience, but there are a lot of other factors that evidently explain the remainder of somebody's salary. Okay, now just as a comment, there's something else called the adjusted R-squared that people tend to ignore. The R-squared is based on all of the data. The adjusted R-squared takes the degrees of freedom into account. The adjusted R-squared is always going to be lower than the R-squared. And in fact, if you take this to its logical extreme, I'm finally going to use my pen here. Let's suppose that we have years of experience and salary, but we only have 2 observations. All right, these are our only 2 observations. Well, obviously, you can draw a perfect line with only 2 observations, but the degrees of freedom here is going to be 0 because we have 2 observations minus 2 for the intercept estimate and the slope estimate. And because we only have 2 data points, our R-squared is going to be a perfect 1 by definition here. But the adjusted R-squared is well, I forget. I think it's going to be 0, or possibly even undefined. I don't remember what the exact definition for the adjustment is there. But the point is that the larger your data set is, the closer the adjusted R-squared gets to the R-squared. The adjusted R-squared will converge to the R-squared in much the same way that the t-distribution converges to the normal distribution as your number of data points gets larger and larger. Okay? So there is no there is no answer to the question, is this a good R squared? The R squared just is what it is, and then it's a question of deciding, so is this model of use or is it not of use? For making predictions about individual people, in this case, individual people's salaries, this model is, maybe of some use, but we are aware that it's going to be far from perfect. If we had, a much larger sample, if we were sampling salaries over, many, many, many companies, then our R squared might give us a better, our R squared might be better in terms of figuring out dependencies of average company salaries as a function of years of employment among a whole bunch of companies. But for doing models trying to predict things about individual people, typically these R squareds are not going to be very close to 1, meaning in this case that years of employment is not the sole determinant of somebody's salary. Okay, so these tests of understanding here basically ask you to repeat the kind of analyses that we did in this module, but using a different explanatory variable. That is, we want to get a regression that explains or computes or predicts salary as a function of years of education, rather than as a function of years of working with the company. All right, and we'll get a slope, which will tell us how much each additional year of education increases salary. We can then ask at a 0.05 level of hypothesis testing whether education increases salary at all. Okay, here we're testing whether we're testing the null hypothesis that that the effect on salary of education is 0. Next, we're testing at a 1% significance level whether education increases salary by more than $2,500. Okay, now in this middle one, the 0.05 level that tests whether education increases salary at all, you can simply use the t-score directly from the table. In this next one, you're going to have to compute a t-score yourself and determine whether that allows you to reject the null hypothesis at a 0.01 level of significance. And then finally, we're asked to compute a 95% confidence interval. So these are all repetitions of the various examples that we looked at in this module, but using years of education rather than years of working with the company.